Hello, this is part 2 of my advanced button tutorial with Wiring Pi and Raspberry Pi. In part 1, I talked about the setup and current status of the Wiring Pi library. This part is dedicated to the code, so let's get on with it. Header files first. Wiring Pi is needed to operate the LEDs and accept button input. It also has a number of additional features which I will use in this program. POSIX threads will be used to blink one of the LEDs asynchronously and indirectly include the time header file. My program will handle a number of Linux signals, allowing it to shut down cleanly by restoring all GPIO ports to the default state. Program control will also use the exit and pause statement available in the last two header files used. I will use BCM numbering in this program. As there will be 6 GPIO pins used in multiple places in the program, it's worthwhile to define them as constants. This will make it easy to change if needed in the future. I want to make sure that the operating system signals such as Control-C or kill are handled correctly. This program will call a subroutine called cleanup whenever one of such signals is received. The cleanup subroutine will set all 6 ports used to the default state. All LEDs will be turned off, the ports will be reset to input, and internal resistors for button ports will be set to pull down. The program will terminate afterwards. The Wiring Pi setup GPIO function will prepare the GPIO ports for use following the BCM numbering scheme. The button and LED pins are configured next. Although input is the default state for GPIO ports, there's no guarantee that they are in that state when the program starts. This is why I explicitly say so before activating the internal pull-up resistors. There's also no guarantee that the LEDs will start in off state. This is why I set the state initially to that. As is, this program will end after initializing the components. I will use the pause statement to stop the program here until a signal is received, triggering the program termination. This is the basic setup, and we are ready to define the functionality of the first button. Let's start with red. YouTube is full of Raspberry Pi tutorials, but most of them show how to use buttons incorrectly. In most cases, you will see an infinite loop which continuously checks the button state and calls a function when the button state changes. Something like this. This loop will change the red LED state based on the red button every 50 milliseconds. Let's compile it and see it in action. Make sure to use the Wiring Pi and pthread options with the compiler to match the header files included at the top of the program. This infinite loop approach works, but is very naive. The program is trapped right now inside this loop, effectively preventing me from implementing additional features tied to the other buttons. Normally, this is overcome by using multi-threading. You could implement this straight up using POSIX threads, but Wiring Pi has a simplified interface to threading, which it calls interrupts. That is actually very neat. Let's fix this program. First, by moving the blocking code into a subroutine. This subroutine will become the callback for the red button, which will be executed every time the button is used. Threading in general and Wiring Pi interrupt specifically can run any code contained in a subroutine concurrently to the main program. The clunky loop is actually not used in this model, as the continuous communication between the button and LED will be handled internally by the Wiring Pi interrupt model. The GoRed subroutine needs to be registered as the callback for the red button using the Wiring Pi ISR function. You have a choice to trigger the callback for rising, falling, or both edges of the button signal. I will use both edges in this case. You can only register one interrupt, and you can only pick one edge type per button with Wiring Pi. If you try to define more than one interrupt per button, only the last interrupt declared will be active. It's important to realize that the GoRed subroutine will be called only and if when the button will be pressed or released. With the interrupt model in place, I can easily add new functionality tied to the other buttons. Let's make the green button toggle the green LED state. The green button setup is very similar to the red button, but I will configure it to respond to the falling edge of the signal when the button is pressed down. Releasing the green button will not have any effect. Let's write the Go Green subroutine now. Notice that although an LED is an output device, its state can be read. I will not add the delay here to demonstrate what actually happens when a button is pressed. You probably noticed that some of the button presses did not seem to be working as expected, and the LED does not always toggle correctly. This is due to the fact that the button mechanism actually bounces multiple times when it's pressed. What seems to my finger as a single press, the computer sees as a series of presses and releases. The button will settle to the solid contact within a fraction of a second, but the transitional period is a problem. The program needs to account for that and ignore the vibration until the connection is solid. The 50 millisecond delay used in the Go Red function took care of that to a degree, but WiringPi queues 2 interrupts, so in most cases the Go Green subroutine would be called at least twice with each button press. In some cases, the button will not be settled with the first call yet, causing the LED to revert to its original state with the second call. This cannot be solved by introducing or even increasing a delay. I need to write a dedicated function which will debounce the button. There are different ways to go about it, and I will use the time method here. The isPressed function will use a persistent variable to remember the timestamp when the button was pressed last and compare that to the timestamp of the current press. The clock getTime function provides time accurate down to a nanosecond. The program will calculate the time difference between the last and current button press with that accuracy. The value of 5 I use here was determined experimentally with my buttons, and it gives me a good balance between button sensitivity and missed bounces. You may need to adjust this value slightly up or down in your case. A higher value will make the debouncing process less reliable, but it will make the buttons more responsive. This debouncing function will return true only if the button presses are far enough apart based on above time calculations. You can see now that the button presses are more reliable, and in most cases they get registered correctly. Let's move on to the third button. I will use the blue button to activate the blue LED for a blinking action. The same button will be used to start and stop the blinking with consecutive presses. The blinking process itself is very straightforward. You take an LED of your choice and turn it on and off repeatedly based on a delay. Introduction of an infinite loop calls for a new thread, separate from the WiringPi interrupt that activates it. The separation is necessary as the interrupt shouldn't call such subroutine directly, as it would never come back otherwise, and you would not be able to stop the blinking once started, at least not with the same button. WiringPi has a simple threading interface, but I find it too limiting, so I will use POSIX threads directly to implement the blinking. POSIX threads execute code defined as a void pointer to a function which must accept a void pointer as a parameter. Obviously, my blink function is not defined that way. The easiest way to go around that limitation is by creating a wrapper function that fulfills the void function pointer requirement around the code which needs to be run multi-threaded. This, however, results in a compiler warning as the callback function is expected never to return. My blink function itself works that way as it is an infinite loop, but the wrapper approach does not convey that information to the compiler. You can add a return 0 statement to the callback to get rid of that warning. Time to write the Go Blue subroutine. This code will be called every time the blue button is pressed. A static variable will keep track whether the blink thread is active between presses. If it isn't, it will be created and it will indirectly call the blink subroutine. If the button is pressed while the LED is blinking, the thread is stopped by calling the thread cancel function. The thread ID tracking variable is reset to 0 in preparation for the next button press. The LED needs to be explicitly turned off just in case the thread was terminated mid-blink. This works great, but can LEDs be controlled in a different way? For example, through holding a button instead of pressing it? Let's replace the standard is press debouncing condition with one that will do that. I will use a sampling method to accomplish this goal, which is another method to debounce a button. This function will read the button state repeatedly over a course of a predefined time period. If the button state is unchanged throughout the sampling, the button will be considered as being held. The way my function is written, an example 1 second hold will mean that the button will be read every 25 milliseconds, which will take about 1 second to complete altogether. You may need to adjust these parameters to match the buttons you have. The loop used here is short-circuited, where the sampling will terminate as soon as a button state change is detected. Effectively, all regular presses and all holds shorter than the predefined hold time will be ignored. This function will return true if the button was sampled successfully as having the same state. That is all for this tutorial. If you liked this video, please hit the like button and subscribe. Thanks for watching.